quite a large group of ranging from dynamical aspects like Vincent Delecroix or analytic aspects like Carl Peterson to more theoretical aspects, computer science, informatic theory aspects like Dominique Perron. I will present a family of subshifts, the so-called Dendric shifts, Dendric worlds, and then I would like to stress here the connections which are numerous with group theory. So I will explain what I mean by this family of symbolic dynamical systems, the Dendric ones. They are described with easy combinatorial restrictions on their factors. And in this lecture, I want to stress the fact that they will tell us, they will give us information on free monoids versus free groups. For instance, they will allow us to provide positive basis of the free group. And I will go, if time allows, toward group properties, group theoretic objects associated to these dynamical systems like dimensional and discussions on skew products. Okay, just for the vocabulary, so I work with symbolic dynamical systems, that is to say with infinite worlds. Here they are one-dimensional, but just a detail. It's just because I will iterate substitutions to generate them, so I've stated everything in terms of one-dimensional worlds. And just for the vocabulary, a subworld, a factor is some subworld that you can see in an infinite world. So here you don't see 2B in a world, it's not factor. You have a dynamical system, the dynamics of the shift, which raises one letter, and then you create symbolic dynamical systems by taking iterates of the shift and the closure, and you get something which is closed and shift invariant. It's a symbolic dynamical system. So if I'm given an infinite world, I can create a compact set on which the dynamics of the shift map acts. That's a symbolic dynamical system. And then, in general, what is a shift? It's a closed shift invariant subset of my set of sequences on the finite alphabet A. And then this definition means, in fact, the topology, which is the product of the discrete topologies on each copy of A. So that's to say, two words are closed if they coincide on the beginning. So it's not difficult to see that shift is completely described by its set of factors, the worlds, the subworlds that you see in some elements of your set of infinite worlds. And we will work with minimal subshifts. That is to say, they are minimal in the sense that each time you take something which is inside the shift, which is closed and shift invariant, it's the full set if it's non-empty. And another way to see that is to say that you take sets of infinite worlds, and all these infinite worlds have the same subworlds, the same factor. So that's a shift, a set of infinite worlds. The dynamics is given by this map, which erases the first term, and all these infinite worlds, in all these infinite worlds, you see the same set of factors. Is it okay? Or... Okay, no, I will start with always the same example. I'm really sorry, but it's always quite illuminating to see this example of the Fibonacci substitution. So this is the substitution is a way to create infinite worlds, to create symbolic dynamical systems. Okay, so I start with the Fibonacci substitution. It's a morphism of the free monoid. So with respect to the free group, I don't have cancellations. So I can define such a map just by giving the images of letters. So I replace letters by words, like what is given here. And by iteration of this map, you see that you converge toward an infinite world, which is a fixed point of this map. So I start with A. Since the image of A starts by A, it gives you when you take the image of A, AB. But then, since the image of A contains so this A, sigma A is a prefix of sigma squared A, or sigma squared A, and so on and so forth. So we have a sequence of nested prefixes. So with the topology, the word topology, this gives you an infinite world. This converges towards a sequence of infinite worlds, and this is a fixed point of this substitution. The matrix that we can associate with the substitution that I will draw here. So this matrix, I just put in columns the images of vectors is such that this matrix has a, if you take the square, it's a positive matrix. Okay, you have you can use term Frobenius and all this machinery, which tells you that then you create, I'm sorry, you don't even need the term Frobenius so far. It's not difficult to see just combinatorially that the fact that this matrix has a positive power for which all the entries are positive, gives you that your system is minimal. So if you take any, with this infinite world, you take any other shifted image, you take the order of these shifted images, you will get a world that has the same set of factors as this infinite world. So we can associate with such a substitution a shift closed shift invariant subset X sigma. And then my point was to say that we have a lot of properties related to group theory and to the free group. So just to see such property, let's look at factors of a given length. And then the property I want to express here is that factors of a given length generate the subgroup of the free group generated by factors of a given length. In other words, I look at factors of a given length here. You find A followed by A followed by B followed by A. You don't find B in this sequence, and you can check it. And to check such things, we just use that U is equal to sigma of U. Okay, so you will never be able to see a B because the B are always preceded by the A. But from a group viewpoint, BB can be recovered from BA and AA. Let's see with words of length 3. Let us see whether the missing words of length 3 can be recovered in the free group from the 4 words of length 3 that you can see in U. Well, that's indeed the case. So here you use directly the words that you had. You create a new word, and here you might use this new word. So the first algebraic property that we have with this substitution is that the words, as I said, the words of given length give you a basis for the subgroup by words of a given length, and also a positive basis. First property. Okay, so this is a result that has been observed by Berthé, the Fibonacci lemma of not only for the Fibonacci world, but for so-called Sturman worlds, which generalize the Fibonacci world. So that's the property we see. If you consider this subgroup of the free group generated by words of length n on your alphabet, then you get a basis with the factors of length n of the Fibonacci world. And by the way, there are n plus 1 factors of length n, so that gives you a basis with n plus 1 elements. Well, that's the beginning of the story of the so-called Dendric worlds. But then you might think it's very specific to the Fibonacci substitution, because it's not difficult to see that it's not only an object which lives in a free memory, but it's also an object that seen in the free group is invertible. So it's an automorphism of the free group for this specific shape. So you might think that this property has to do with the fact that it's an invertible substitution of the free group. So my point here will be to try to go beyond this property and to see to demand something more, to see which combinatorial properties can we have to capture to have such results. And I give another example of a property, an algebraic property of the Fibonacci world that we will use a lot, which is given in terms of return words, return times. exactly as a return time in dynamical system when you induce some subset and you want to see the return time of a map. So that's the same idea. So we are in a case where minimality means that factors occur with bounded gaps. So if you specify a factor, the value, you see it occurring with bounded gaps. Pardon, merci. Yes.
The previous theorem, that is called for our arbitrary Sturm rules.
Exactly. Yeah. So that's a property of Sturm rules. So it's true for arbitrary Sturm rules. And if you respect to substitutive Sturm rules, the substitutions are invertible. So the question I raised about is it related to is it just a question of being generated by some automorphism with free loop is still can still be asked, even if we know that it's true for any Sturm world. And the next property will be also true for any Sturm world. So the point is how can we go beyond the Sturm worlds? What properties can we capture to go beyond these things? Thank you, Pastor. So yeah, so I was discussing return world. So a return world is just a return time of a given world, the value. That is to say, if you specify the value, a return world to W is some world V, so that WV starts with W, of course, but it contains an occurrence of W at the end, and exactly two occurrences of W. So for instance, if we want to see the return words to A, we are looking for a word such that A concatenated by these words contains two occurrences of A. So for instance, A BA contains 2A. So that's what we call the return word. So we put bars after each occurrences of the return words. Is it okay? Yeah. So we have this way of decomposing an infinite word. And then if we look at what happens for the first words, we find two return words. And once again, an algebraic property. The return words form the basis of the free group. So just check it with here, this case of return words on AA. So you find the word AA, BAA, the word AA, BA, BAA. So it's really return words to A. And then you can generate the letters of the free groups with these two return words. So once again, this is a property that tells you with this combinatorial object, the return words to some factor, we can give positive basis this time directly on the free group.
Right. Is it a free basis?
It's a yeah, exactly. Not only it's really a basis. It could be a generating set, but here we have the miracle that it's not only a generating set, but really a basis. So it's not just not for fun. It's really very important, very nice as a property, because then you can recode in infinite world. You take its first letter, A. You decompose it as a new alphabet, given by A, B, A. Let's call it A, capital B. This gives you a new word, which can again be substituted, which has also this nice property if you start with Fibonacci or a Schumann word, as you mentioned. So that gives you a nice way of decoding infinite words. And this is the core of all the results I will present on classes of infinite words, which will have this nice property. They can be decoded with as many return words as the alphabet, which form the basis of the free group. This decoding will create matrices in GLD of M. And this decoding will allow us to give a lot of properties, ergodic, combinatorial properties on these infinite words. And we will see what we can do with that. So, what we have in this case is every word has two return words which form the positive basis of the free group once again. So that's for the Fibonacci word. And then I arrive now to the notion of Dendric shifts. So this idea was to find infinite words which would have this kind of nice property. So we are trying to capture what what makes things work. Is it on being Sturmian? Is it being fixed point of homomorphism? And you see that it's a property which is combinatorial in nature that allows us to capture this Gutenberg property. So I will have a few combinatorial slides. And then I want to convey the idea that the property we're looking for is really combinatorial and has no extension of factors. So we take a minimum shift. We take a word, and we look at the letters that can prolongate, expand these words on the right, on the left, and on the two sides. And we will make a graph. For each W, we take as vertices the letters on the right and the left that extend this word, and we put an edge if we have the two letters which extend this word. That is to say, that makes a graph like that. I forget the idea of the W. I've got an edge between A1 and BK if you can find A1, the word W, and BK. Okay, so that's just a graph. For any word of your language, you make a graph which has whose aim is to capture the prolongation, the possible prolongations in the past and in the future that you can make given a finite word. And then the term Dendric comes from the fact that the property we're looking for is just the following. We want this graph to be a tree for any word. This is to say just being connected and acyclic. Well, it's an undirected tree by graph by definition. So maybe we come back here. We just want to have this kind of shape for the extension graph. So at first we called them three sets, and then we saw that there was an ambiguity with a language of three languages. So we moved to Dendric sheets. So that's the property we studied. And then we will see that it captures, as I said, the properties of Fibonacci words in terms of William words. So that's our definition. So just to warm up, consider an example which is not dynamic. So instead of taking the Fibonacci substitution, take this automatic sequence, 2-month substitution. Then here, if we look at the word 0-1, then 0-1 can be followed by all possible combinations 0 and 1 and extended by 0 and 1, and all the combinations are possible. So here it's not a tree, we have a cipher. And here we have something which is not connected. Well, that's not Dendric. We have too much choices in the extensions, and here, since we have two disconnected components, they live their lives. So we really need something connected and not too much freedom in the possible extensions. So that is not Dendric.
Several trees you don't consider as trees, so a forest is
No,
not
exactly.
that.
So we consider forest for the empty world, for the beginning. We have some cases where if we start with the empty world, we have two disconnected components, and after that they behave well. So that's the only forest we can consider. Or we consider eventually Dendric words, so the words for which after some stage we are not a forest but a tree. And then for Fibonacci, let us check that it works well. For the empty word, the fact that we don't have D followed by D makes you something nice. And then for all the letters, we have something which is a tree. So that's really the property which will be super useful to make a propagation information algebraic and the deep combinatorial information inside of it.
The properties for some W or for all?
All W. Or or maybe not for the like here. So as I said, maybe for the empty world, you can have two forests and a forest. And then ultimately we can also undo stuff if you use the right integration.
So you ask for all words of them at least one, you have a tree.
Yeah, for all words, yeah. In this lecture,
Except of the empty one.
Exactly. We want this really So of course it makes sense for the worlds which it's interesting when the world has two possible extensions, several possible extensions on the left and on the right. So yeah, that's where it makes sense. So just to, so I introduce a definition. So is it really so interesting? So it captures Sturman worlds. That was your question. So Sturman worlds are worlds of factor complexity n+1. They are codings of Toro translations. So it's a classical family of worlds which come into this family. Something which is interesting. So that's the question. Interval exchanges. So interval exchanges come into this family. Arno-Rossi world, which is a different family of worlds, which is super interesting also, which have been studied from a group theoretical also viewpoint by all these people. You have nice results. So Arno-Rossi, of course, Valérie Berthé Dendric also nice result on the Hausdorff dimension and the Rossi gasket and stuff like that. So it's fascinating also world of worlds with nice algebraic and dynamical properties. And then natural evolutions for more interval changes come also into this definition. So what is interesting here is that we can handle from, at least from a symbolic dynamics viewpoint, families of worlds which do not have necessarily the same kind of properties from a dynamical viewpoint, but from an algebraic viewpoint, they have a lot of things in common. Just for instance, they have the same factor complexity, the same number of factors of a given length. So for Sturmian, the Sturmian world d equals 2, we have n+1 factors, and 2 letters, 2n+1, d minus 1, n+1 factors. I think you have a question. Yeah.
Sorry, that property that what is generated can be characterized by its Rossi graphs.
So exactly. So thank you for asking. And I don't remember whether, well, okay, I answer you now. So the property we have by Rossi graphs is that the group generated by the Rossi graphs is the free group. So if you do some silent foldings, you arrive to the decay at the beginning. So you have a sequence of Rossi graphs. Rossi graphs are like the Brownian graphs. I don't know whether they also capture extensions. So you have an infinite series of graphs for all factors of given length, and all these graphs generate the so that's equivalent to this property of to definition.
And what does it mean that the graph generates a group?
So Rossi graphs are you have an arrow between two factors, and one factor follows the other one. So you are not allowed to do, if you follow the dynamics in infinite worlds, you're not allowed to do any path on the graph. Right. So what I mean is that when you forget what you do in the symbolic world, but if you see the graph as all the possible path, the path you can do with respect to the graph, you arrive to the free group. That is to say, you have the right to invert your rows, and you go from a graph in the free monoid labeled by letters. You embed it into the free group, and then this graph, if you the cycles all are allowed to follow with the graph, is the free group.
Thank you. As like another question, but can this property be characterized by only topological kind of these graphs? For example, for Sturmian, what we know that they are characterized that all their Rossi graphs are just a combination of two cycles.
Yeah. Yeah, so we don't, so it's more just here, the fact that you have three possible extensions or two bosons for Arno-Rossi, you have some as nice as Rossi case, case, you have something like that. But then we have factors which are two images and stuff like that, then the topology becomes more complicated. So that the case of exchange of intervals. So that's more delicate to make the zoological classification, but that's something we are looking for. So it's a nice topological characterization of this. And then don't shift, but now let's see whether we get what was expected from the Schumann case. Yes. Again, the factors of length n form the basis of the subgroup generated by A to the n. Okay. And just to check whether everything is consistent. Yeah, yes, that's consistent with the factor complexity I gave you, just by Schreier's formula. The factor complexity gives you the cardinality of such a basis, so it's really a basis. And then let us check. So we are considering a subgroup of index n. So n is the length of the factors, it's here. And then the rank of a subgroup of index n in the free group of rank D is this formula, which is exactly the factor complexity. I've got the right number of elements in my basis. Okay, so that was a remark. Thank you for asking this about opposing halves. Okay, so first result, and then for the written words, which is the one that we explored the most, it's again the set of written words to any word gives you a positive basis of the free group, and then we can decode with respect to written words. So that gives you when you are working towards rapid leadership representations of symbolic dynamical system, we can build them with this written words and work always on the same alphabet. We can have a rapid leadership decomposition given always on an alphabet of cardinality D, the initial alphabet. So that allows us to decompose and to understand this kind of symbolic dynamical systems as any way you want to decompose it, as I said, working towards rapid leadership, acidic representation, any kind of representation you want by decomposing.
So there's a notion of rank for dynamical systems, right? Essentially the number of towers you need.
So exactly. So now the rank is the cardinality of the alphabet. Exactly. So what this combinatorial property of Dendric shift tells you is that you are of rank D, you have D towers to express your dynamical system, plus information on your matrices from each rank, and they are invertible. But it's even more than that. It's that the morphism that you will allow from one rank to the one, from one level to the other one, are group automorphism. So it's super interesting algebraic property. So you can, so maybe you're not substitutive, you have no reason to be substitutive, but you can decompose your system as composition of group automorphisms. For people who have in mind the model of interval exchanges, a Rossi induction gives you invertible automorphism, invertible matrices. So you have the same kind of object as what the model of Rossi induction brings you here through written words. And then when I say that in my family you have interval exchanges, you might think, and that we were also puzzled at the beginning, we thought that maybe these algebraic properties would come from the parts which is behind the geometry model, which is behind. We were in fact capturing algebraic properties of the vacuum dot flow and stuff like that. But in fact, no, we have other families for which we have no geometric representation. Like no flow, no geometric object which underlies these families of modes. So these are properties of the Dendric words. And then from a dynamical viewpoint, we can ask what kind of properties this brings. So let's start with the example of 3 letters. So we have now a nice property which says that if the factor complexity is small, the sup of the number of factors divided by n is smaller than 3, it gives you unique ergodicity. Unique ergodicity, so I don't know whether it's you are fluent in unique ergodicity. So it says that on the dynamical system that you have a unique way of putting a measure which is invariant with respect to the dynamics. So it will play the role of the R measure if you are on a group. It's a translation of the group. So you have a unique measure that you can put, which is invariant. So that's quite strong in some sense because combinatorial statement, topological nature, few factors, not too much factors, subwords gives you a major theoretical statement, unique ergodicity. If you prefer, it says you also that the words that you have are nice distribution properties. The factors occurs in a way that you can compute their density of equivalency, their frequencies, and you have uniform convergence for this kind of object. So on an alphabet almost of size almost 3, this Dendric property gives you this unique ergodic property. But then it's not true for higher dimension because we know that we have interval exchanges which are pathological in some sense, in the sense that they are not uniquely ergodic. And then there's a result by Dendric and Kenscher that shows that, okay, you are maybe not uniquely ergodic, but you have finite, well, you have an equivalent on the number of ergodic invariant measures you can have, given. Okay, so these are the kind of properties that your systems have. So they are maybe not as well distributed as uniquely ergodic, but they don't let too much space for the number of ergodic invariant measures that you can have. And the proof of the paper of Dendric and Kenscher is based on the Rhodes graphs. It's a very nice paper on ergodic measures. And then another result, recent result I find super nice also, it's due to Kreutz and Pavlov, and they say that if you have even more restriction on the factor complexity, if it's smaller than 3.5, then you are translation of compact Abelian group. Then you have pure discrete spectrum from dynamical viewpoint. So I think it's a really nice result and quite unexpected in some sense, giving once again a relation between factor complexity and some dynamical property. So my from the beginning, I'm trying to see connections between this family of individuals and group theory. So here you have a connection in the case where the complexity would be small. So for instance, that works for Sturmian worlds. Sturmian worlds are translation in compact ability. But Dendric worlds have a larger factor complexity in general, so it applies only for restricted family. But I just wanted to quote these results because it's quite interesting to see how a result on the number of factors gives you spectral information.
I ask you, how optimal is the DST over 2? If you this statement, this theorem says if smaller than 3 and 2, then it's translation. And if you have something greater than 3 over 2,
yeah, it can. It's a sharp.
It's sharp.
It's very sharp.
Even exactly 3 over 2.
Yes. Yeah. In the paper they gave that it's very sharp.
So generalization of extension of translation of
I don't know what they had. Yeah, you're right. Is it a question or
no, it's a question.
Yeah, I don't remember. In fact, yeah. No, I think it's really weak mixing, and they prove the absence of that they prove the absence. It's weak mixing, so yeah, they really have a. So for the remaining time, I would like to go into two other type of properties of these Dendric shifts. And I went into the direction of dimension group. So dimension groups is an algebraic object that you can also associate with symbolic dynamical system. And the aim of dimension groups is to capture orbit equivalence. So I will explain this in the next slide. But just as a warm-up, this is a group which corresponds to the set of continuous functions defined on a shift. For instance, take an indicator function of the letter A. You find the letter A in some infinite code. And then you take the question with respect to so-called coboundaries. The coboundaries function like F composed with a shift minus F. So that's a group of continuous functions. So why do we take the question with coboundaries? I don't know whether Gottschalk rings a bell for you. Well, this is the theorem which says that if you have a bounded ergodic sum, then you are a co-boundary. Ergodic sum, so by ergodic sum, I mean something which has the form, some of these form, you have a dynamical system. You have say a solution, and you want to follow. Pardon?
Par des sommes, pas de moyens. Enfin, sur elle, pour le projet.
Je veux dire que ça va être misleading d'avoir divisé par n. Ouais. Alors, ok, donc on va dire, oui, t'as raison. On a une moyenne. Et puis le terme ergodique nous dit que les moyennes, quand on divise par n, on converge vers l'intégrale de la fonction. Et de chaque ennemi, divisé par n, on va converger vers, si tout va bien, vers l'intégrale de cette fonction. C'est un ergodique. Mais Gottschalk et Lee nous donnent des résultats sur les sommes non divisées par n, les moyennes. Et la question de Gottschalk et Lee, c'est de savoir, je parle en français, excusez-moi. So Gottschalk and Lee tells us that if you consider this means not divided by n, you want to see whether they are finite or bounded or not, and to be bounded means that you are a co-boundary. So that's a kind of explanation of why we take things modulo a co-boundary. A co-boundary cancels when you take an ergodic mean. Okay, so that's the dimension group. And then with my two favorite examples, the Dendric one, the not Dendric one, we have in one case that this group is Z squared, and in the other case, the group is Z of 1/2. So that makes you two different groups. So what I want to illustrate with this is that with the case of Dendric worlds, this property that we see, the extension property, the rosy graph property, will be captured in the fact that the continuous functions, the set of continuous functions modulo boundaries, is a very simple group, is ZD. You have a kind of independence. Another way of stating that is to say, once you know the frequencies of letters, the frequencies of factors are related to the frequencies of letters. So this extension property can be expressed in ergodic terms in this sense. This is a property you have also for interval exchanges, which is well known. If you fix measures with respect to the values on the one-letter cylinders, then they coincide. So that's what I want to convey with this idea.
Is that with one graph as an editable group?
So, yeah, exactly.
Isn't it the same as that?
The same as
that?
so I mean, no.
That's adjoint 1/2.
Yes.
So all
That
powers
will
of
be
1/2.
Z of 1/2. So you have one. You have 3/2. Z is included strictly in this.
It's polynomials in 1/2. It's polynomials in 1/2.
It's known as one graph.
Like yeah.
Not finitely generated.
And the 1/2 comes from it's a consonant substitution, automatic sequence comes from the length of the substitution. So more on dimension group. So the idea is to capture orbit equivalence. So orbit equivalence is when you have two systems which have the same orbits. You don't take the closure, just the same orbits. Two systems are orbit equivalent if you can send them. The homeomorphism, it's topological motion, orbits to orbits. Okay, and then you can refine the notion. You can try to understand the map that relates one orbit to the other one. So that's the cycle. So when you apply your map which transfers the dynamics from X to Y, when you apply one step T here and here, then you jump into the other orbits, but not with the same, you haven't jumped in the same way, otherwise it would be a topological conjugacy. So you have a map, and the point is to understand the regularity of this map. So strong orbit equivalence is when this map, which tells you how to jump from one orbit to the other one, inside the other orbit, via your map H, your homeomorphism, which transforms the dynamics. then if this map is regular, only one point of this rigidity is called strong orbit equivalence. So it's topological notion, and it's not measure theoretic in the sense that if you take something too loose, I mean, if you are in a metal relative sense, then everybody is orbit equivalent. So I really stress the fact it's topological notion. And then we have a nice property which says you that you have an object, the so-called dimension group, which is another group based on this set of continuous functions, which tells you that, I will come back to this, strong orbit equivalence means that you have the same dimension group. So I come back here to the dimension group. You take these continuous functions, you do boundaries, you have a notion of order given by function with value here in n. So you have another group, and this is the invariant for strong orbit equivalence. So this is this group. So now, from a concrete point, we will take continuous functions, we will do boundaries, functions with value in n, the constant function equal to 1, and we will try to compute this quantity for Dendric shifts. And then we see that we can do it. And then the result we have for the Dendric shifts is that this noise property of extensions makes your group easier, and so that it's just Z to the D. It's again the same property of having a basis of 90 in some sense, independence of letters. So you have something which tells you that your continuous functions are defined just once again on letters. You have a part which corresponds to the different ability measures, and you have a complete description of the dimension group. So it's a bit technical here, and so you are not maybe thrilled by this information on the ability measures, but I just want to stress for the algebraic part at least that it's another way to recover these algebraic properties that we add dynamically, saying that because here we are touching ability measures, we are entering into not only topological combinatorial properties but analytic properties. So this algebraic description of the algebraic properties of Dendric shifts can be seen on this invariant, dynamical invariant of orbit equivalence. And then just as consequences, for instance, if I give you two Dendric shifts and they have the same frequencies of letters, well, they are orbit equivalent. Also, they might be completely different from a dynamical difference. So inside my class of Dendric shifts, as soon as you give the same measures to one letter cylinders, the same dense frequencies of occurrences of factors, then you have orbit equivalence. So this combinatorial property has a meaning in terms of orbit equivalence. Also, in terms of properties, we can have, for instance, exchange of point intervals which are not uniquely ergodic and Amorosi was always uniquely ergodic. So that was a kind of property I wanted to stress. Then I had some few elements on street products, but I think my time is over. So I'm going to jump to the conclusion. But Dendric words. So they were really algebraic for me because as properties that we've seen, Newton words generate the free group. They provide the basis of subgroups of finite index, and also something I want to stress that because at the end, if you take a street product of a Dendric word with something which goes into a finite group, you get linearity, you can get abelicidity. So in some sense, it leads you to what I call profinite equidistribution properties, which is just as a teaser on further properties of the Dendric breaks. I'm going to stop here. Thank you.
Thank you very much. So you did end up, oh, precisely on time, the second. Now we do welcome questions from the audience or, yes, Kostya?
You had an example of dendritic words, like Schumann words, the big words, and so how much is this list of examples?
It's not exhaustive in the sense that I can combine with this kind of description. So this is the literary chamber. This is the harmony. And then if I've got more letters, I can really make something more subtle in terms of possible extensions. So this is so I've got a colleague, Julien Laurent, was made a kind of graph of possible posigraphs, and then we see that we have in some area rosy interchange, but the majority of non-words belong to this family.
It's really interesting. You look like all other dendritic words, look like other stuff, like a combination of this, for example, or there are also there is something also completely different.
Yeah, we have a family called Cassien-Selmer, which comes from Selmer continuation algorithm, which is completely different. But the questions we have is in these strict strings, rosy intervallic change, we have a nice geometry we know how to describe them. So we would like to understand the rest in terms of geometric representations. We have the thing that with the formalism of Lustig and people around the master Lustig, that would be real tree. They have nice formalisms, geometric representation of automorphism. So we have the thing that we could understand the words with algebraic representations in terms of trees. For this object.
So this, I didn't understand this orbit equivalence. So does this, maybe naively, does this allow if I have two dynamical systems and I want to know whether some iterates of one or the other coincide? Does this orbit relation allow me to?
So you want to see T square, is T square equal to
V30? Yes. Is this the why how I should understand this orbit equivalence?
So you say we have is it the necessary condition to be equivalent to
Yes.
This one and more time to this. So like that, that's so yeah.
I had a question, which is, I was wondering from the beginning, do you have an intrinsic characterization of being a dendritic system?
So what we are on plan for this is to say that if the written words generate from a basis of the free group for every W, we want to say that it's a characterization of.
Yes, but that's not intrinsic in this. I give you a compact topological space and a self-map of the space. And I ask you, is this dendritic? You don't have words yet. There are very different ways of encoding it as words. So is there a...
So for the Shannon case, do you have such an intrinsic description? We'll start with this.
Well, they do correspond to rotations on a one-dimensional torus by an algebraic number of degree 2.
But then, yeah, we won't have such nice answer.
So in that case, yes, it's well, no, maybe it's even more complicated. So they have an equicontinuous factor, which is that, but then there are very different ways of blowing it up. So it's really always bound to one representation by words.
Yeah.
And to continue what, so who is suggesting this?
Maybe the answer to this question is too specific, but please explain anything in more detail. Suppose we know a rosy graph for some n, for a dendritic shift. Then, if there are no special vertices, then of course we know the next on the graph. And in the case when there are the special vertices, could you please explain what can happen in these vertices? So which possibilities are forbidden?
Forbidden, I can't tell you like that, but anyway, yeah, there's a graph of topological. So you have to look at the paper by Julien Leroy and France Gerhardt. So they really made this graph of graphs, and then they tell you what is allowed in the possible extension topology counts. It's your question.
Yeah, it's,
So the creators, they have clarified the zoology, they have a paper any kind of canality, but already on the three letters, yeah, you can follow the graph of graphs. So not everything is possible from N to topology of N to the topology of the next evolution of the graph once you have met the special factors. But yeah, there are some restrictions. And then in the three-letter case, the possibilities is described by a Buchy automaton of made of graph of topology of scales. For the descriptions, it's kind of regular, but what's a Buchy acceptance, but you have something like that saying what is allowed in the combination of. I'm not sure if you have a question.
I think some just waiting to understand some definition. I'm not sure I understood everything. Could you remind again what are return words?
Return words is like a return time. You see a letter, for instance, and you want to see it again. So it was a bit complicated in my formulation, just because sometimes you have overlaps. But the intuitive idea is you see a word and you want to see one.
But you see where in your iterations or
No,
your
infinite.
you see somewhere some word, for example, BA, or actually first you see BA here on the left, and you wait when you see it again.
Exactly. So you are at the level of your infinite word, and the dynamics is the one of the shift.
And return word meaning if you have it once, you will have it again, or so what is the return word?
Return words, maybe like a return time. If you think of your cylinder and you iterate your shift until you come back to your cylinder associated with the world. So
yes, but the definition, you take a word, you want to say, is it a return word or is it not a return word?
yeah.
And return word meaning you will see it again and again or something else?
The world, no, you see once. Just you have it in the world. You wait until you see again your world, and any possible combination of letters you see when you see your world is called a return word. And then you have possibly many return words.
And can one see, for example, on this example, are there some words which are not return words?
Of A, because it's a return word of W. So given W, I want to see its possible return words. Now, if I take ABA and BABA, it's not a pair of return words of something. So to be a return word, you're asking what is the constraint of being a return word? So not
Just to understand the definition better, just to want to see an example what is here.
Well, in fact, with the theorem, we know a return word has to be create a basis of the three groups. So
Yes.
if I can maybe find a counter example, if I give you two return words, I don't give you a basis. It's not a nice answer because I can answer with two. But ABAA is always followed by D. So it's not a return word of A. So A won't be the J because we don't have three A's. So it's not a return word.
And you had a statement there saying that something, so that return words from a basis, right, for a free group, under some assumption or new dynamics, or what was exactly the statement?
For Dendric shifts?
For the, and he said it's if and only if, or no, it's not.
It's not proved.
It's not proved, but
This
you
is what
think
we
that
believe.
it might be that it's actually a characterization of that.
Also, I had one more question.
No, you said it, but I just want to check that I understood. The Rosy induction is going from AB to return to a pair of return. What's the analogous of the Rosy induction in the lab?
The decoding with respect to return rows. Exactly. Yeah. You will create the substitution that you will create in one step of Rosy induction. The image of letters exactly are your return rows.
Well, thank you very much, Valérie. We have just 4 minutes till the next speaker. Maybe we should give ourselves 5 minutes break to get a little bit of oxygen. Thanks again.